Okay, so today we're going to work on constructing a new type of confidence interval. And so yesterday what we dealt with was x bars. So we constructed confidence intervals of x bar and did plus or minus the z star with our standard deviation, which was the population standard deviation divided by the number of samples. So that was yesterday's. And the big key piece of information that we were given yesterday is we were given the population standard deviation. Today's distribution and moving forward, we might not have the population standard deviation. So let's read this through. It says a large bakery wishes to estimate its average consumption of flour each day. It sampled over 10 days and found that their daily average usage was this, and the amount of pounds, their sample standard deviation was 700. And they want us to give an estimate of the confidence interval. So we can't use this formula because this formula is really used when we know the population standard deviation, and we don't know that. So we're going to use what's called a t-distribution. And here's what a t-distribution does. A t-distribution says, because we don't really have a good estimate of a standard of our actual population's distribution, we're going to give a little bit of degrees of freedom. We're going to actually make the confidence interval wider than it should be to give us a little bit of extra confidence here. So it actually increases the width of the confidence interval. It works the exact same way as before. But instead of having a z star here, we're going to have a t star. And instead of putting the standard deviation, we're going to put the sample standard deviation over the square root of n. Okay. So it is, again, essentially the same thing. It's going to work the same way, except this t star is actually going to be a little bit bigger than a z star. So I can show you what a t-table looks like. It looks very, very similar. But we do have this thing on the side. It says df. So we're going to talk about that. It stands for degrees of freedom. And the t-distribution is just a wider normal curve that follows based on how big your sample size is. So let's kind of work through this example. First thing that you need to do is we need to check our conditions. So again, we're going to have a couple conditions. We need it to be random. We need it to be normal. And we need it to be independent. We definitely have this thing to be independent because they only took 10-day sample. We're going to try to assume that the population is normal, which we probably shouldn't do, but we're going to assume the population is normal just to keep working through the example. And we're going to assume that the 10 days are kind of random. We're going to say it's not in any kind of season. That would probably make it matter more than the other ones. Like, hopefully they chose 10 good days instead of picking a day that might have an outlier. But we're going to assume those things so we can kind of move through it. In our case, our x bar is 1,000, or 11,400. And we do plus or minus our t star, which we'll find in a second. And then we'll have our sample standard deviation, which is 700, over the estimate number of days, which is 10. Here's how we're going to find t star. T star works exactly the same way as our other confidence interval. For us, we want, for this one, we want 98% to be in the middle, which means I want 1% on either side. But there's one more thing that kind of goes with t star. T star really depends on how big your sample size is, because the bigger the sample size, the closer it is going to get to the actual population. here's how we use the sample size. We're going to use this thing called degrees of freedom. The bigger your population, the more freedom you have. The smaller your population, kind of the less freedom you have. Here's how you find degrees of freedom. You take your sample size and subtract 1. That's how I find my degrees of freedom. My sample size minus 1. For us, our sample size is 10. We got 10 minus 1. So when I go to this table, I'm using 9 degrees of freedom. And I'm going to just kind of go through and look for my tail. My tail, we said, was at 1%. So our T star value would be this right here, 2821. Oops. So we would plug that in, which would be 1,100 plus or minus, and I already forgot what I found my T star value to be. 2821. And then this. When it's all said and done, that would be our final answer. Let's break down a little bit of this. This again we would work out to get our interval, and we would say that we are 98% confident that the true mean falls between this and this. The other thing is this is going to be called our standard error. What your standard error tells you is approximately how far away the average distance is from the actual mean. So the actual mean is about whatever your standard error is to find the different pieces of information. So there's our confidence interval. It acts exactly like our X bars that we did yesterday, except now we just have what's considered T distribution. You have degrees of freedom, which makes your table a little bit different to find your T star. And the reason it needs to be a little bit wider is we have less information than yesterday. So our guess has to be a little bit bigger here, because you don't want to not be as confident as you need to be. So our intervals have to be just a bit wider when we're dealing with T star. We'll use this every single time that we don't know sigma. So every single time we don't know sigma or we don't know the population's standard deviation and we're using some kind of S of X like we are here, we're going to use a T distribution. The last thing I wanted to bring up with this T distribution is this table. Here's a problem with this table. When you look at this table, if you look at the degrees of freedom, it doesn't have every single degrees of freedom. Like let's say you took a sample size of 100, then your degrees of freedom would be 99, and that's somewhere in here. And we don't have that. So the table is incomplete because they don't have every single tail value. If you need to estimate, it's always better to have less degrees of freedom than more. So if we had 99, it's better to go down to 80 than go up to 100. Because you don't want to make your interval too small. You'd rather your interval be bigger and you'd have a higher chance. Well, you'd be more likely to capture the true mean then. On your calculator does this so much better. So I wouldn't actually calculate a lot of these by hand. It's important for you to know how you would find a T star. But by hand, we're not going to do most of this by hand. Here's what we're going to do most of the time. We're going to go to our calculator. We're going to go to our tests. We're going to go down to our T interval, and we're just going to plug in the information. So for this one, we had 11400. We had S of X of 700. We did 10, and we wanted a 98% confidence, and then we would just hit calculate. And there we go. That would be my answer. And then it's done for me. If you need to figure out any piece of that information, like let's say you wanted to figure out like what your margin of error is here. Like you find your margin of error by taking the 1,104 and figuring out how much more you'd have to add or subtract. But that's kind of what we're going to do for t-distributions. Try a lot of the problems today.